Hello everyone. I am about to jump in at the really deep end here. I've been thinking about it for years, but now there's no way back. I've decided to welcome a robot into my house, and we're either going to be very good friends or spend a lot of time grinding each other's gears. At first glance, you might think this looks suspiciously like a board that might control a 3D printer, a laser cutter, at the very least something with a few motors that need some control magic. So, not a robot that'll bring me butter, but absolutely a robot. It won't be squirting out plastic though, as I'm building a printed circuit board assembly robot to do my bidding. A pick-and-place machine. A P&P machine is essentially a robot that takes a bare circuit board and patiently populates it with every tiny electronic component it needs. Imagine you're trying to build a modern smartphone, computer motherboard, or graphics card with a pair of tweezers. Some of the components are barely larger than a grain of sand, some have dozens, even hundreds of connections. A single board might contain hundreds or thousands of individual parts, and every single one has to end up in exactly the right place, facing exactly the right direction. Humans can do it. In fact, that's how many prototypes are still built, but humans get tired, handshake, coffee runs out, and after the 237th resistor, they all start looking suspiciously identical. A pick-and-place machine doesn't have that problem. It doesn't know what a resistor is, it doesn't know what a microcontroller is, it simply knows that component number 143 lives in feeder number 8, needs rotating by 90 degrees, and belongs right there within a fraction of a millimeter. Over and over again. If you've ever watched a 3D printer at work, you'll know there's something strangely hypnotic about it. This is a bit like that, but instead of slowly creating an object from plastic, you're watching a machine assemble the nervous system of an electronic device. Every movement is deliberate. Pick, rotate, place, repeat. By the time it's finished, what started as a blank PCB has become something that can actually think, measure, communicate, or control other machines. And here's the really exciting part. 15 years ago, this was exclusively factory equipment. The sort of machine you'd expect to find in a production line costing hundreds of thousands of pounds, dollars, and euros, hidden behind safety fences with operators in anti-static coats. Today, thanks to open source hardware, affordable motion control, computer vision, and a lot of very clever engineering, it's becoming something a determined enthusiast can attempt to build in a garage. Which brings us to this board. Because every robot needs a brain before it can start building other brains. All cards on the table. For once, this isn't my own design. If I was making my own P&P machine from scratch, this would quickly change from a fun side project to an all-consuming day job. Instead, I've been super happy to follow along as Stephen Hawes has turned a prototype P&P machine into an open source mid-scale manufacturing workhorse. So instead of doing my own custom open P&P build, I'll be leaning heavily on the good work and community and basing my P&P machine build on the Lumen P&P v4 to the best of my ability. Hopefully I have something to contribute back. I've already forked the project and made a few changes to make it easier and slightly cheaper to get manufactured at JLC PCB without lowering the quality. A couple of components had different part numbers for the same part, different parts when it would be cheaper to use a higher quality part instead of increasing the BOM, and then I added a 0.1 inch programming header for easy access, just in case. I could have picked one of the other 10 or more open P&P machine designs, but what spoke to me about this one is the active community, the fact that it's truly open and building one is actively encouraged. And it doesn't hurt that it's yet another excuse to learn to use FreeCAD. Not that I really need to just to build the machine, but I've wanted to try 3D modeling in something other than Blender, which often feels like making gears out of pottery or using a bonsai pruning kit to trim a forest. The other attraction is that it's not just open. It's designed to be made by an enthusiast, not just built from a bought kit, but independently sourced, scavenged, printed, and understood in however much detail you're comfortable with, because every CAD source, every bit of software, and every PCB is right there to tinker with. And that got me thinking. Sourcing parts and PCBs, mechanical components like linear rails, alloy extrusions, sheet metal, and robot parts has changed. So much so that I can almost just add everything to the cart at one supplier. Not just the PCBs, but nuts, bolts, linear rails, 3D prints, almost a whole industrial robot. Even the stepper motors and the power supply. Not that long ago, building something like this would have meant weeks of hunting through specialist suppliers. One company for linear rails, another for aluminum extrusion, somewhere else for fasteners, another for motors, a machine shop for custom brackets, a PCB manufacturer for the electronics. But somewhere along the way, that changed. The companies that used to just make PCBs don't just make PCBs anymore. They machine metal, they bend steel, they 3D print, they assemble electronics, they stock hardware. Every year they seem to do a little bit more. So I started wondering, how much of an industrial robot can you order from a PCB manufacturer? As many of you know, JLC PCB has kindly sponsored a lot of my projects over the years, so I pitched them an idea. Not, will you sponsor a pick and place machine? Instead, I asked, let's find out just how much of one you can actually supply. And to my excitement, they said yes. So this project has just two rules. If JLC can manufacture it or supply it, or I have it already, that's what I'm using. If they can't, then I have to source it myself. By the end of this series, we'll have answered a question I don't think anyone has really asked before. Not, can you build a pick and place machine? We already know the answer to that. The real question is, just how close are we to ordering an entire custom industrial robot from a single manufacturer? Let's start the clock and find out. Instead of just throwing everything into the basket at once, we better start with something I know very well. Let's start with the PCB. There's already a few things I can imagine changing about the PCB, swapping to USB-C, maybe using some cheaper stepper drivers, maybe simplifying a few things, but it looks like a good board that's well thought out. So I'll just add a debug header, since I don't personally appreciate the standard 10-pin header, and remove Lumen PNP from the SIL screen. Not because I don't want to give credit, but simply if I want to sell leftover PCBs, the license requires I don't leave the Lumen PNP trademark on the board. So now it's just a generic PNP motherboard. KiCad has an optional plugin you can download from the plugin and content manager called JLC PCB Fabrication Toolkit, which exports Gerbers, designators, BOM, and placement files in one go in the correct format. So I don't have to think about the details of which layers to plot and export. Just 3 files to upload to JLC PCB. First, I upload the zipped Gerber files, and I prefer my boards in purple with immersion gold pads. Not just because it looks cool, but because the gold finish means excellent shelf life. On the next page, you'll see a pretty close approximation of what the board will actually look like. But don't worry if you see the bottom side is mirrored. That's just how JLC displays it. Next, it's a simple matter of uploading the BOM and the component placement file. Don't worry if it says there's a mismatch between the two. I've noticed that's pretty normal if there are designators without footprints or the other way around. The most important step is making sure the correct parts are selected and every part you want placed is checked. If you're only having a few boards made, it's a good idea to check if there's a basic part available instead of the extended ones, since you pay extra for having the extra feeder loaded. Basically, we're paying for the human labor involved in choosing a special part. Just be sure you don't accidentally pick a part with a lower voltage rating, for instance. The next page is where you get a chance to visually inspect if any components are incorrectly selected and rotate any parts where the pin 1 marker of the package and the footprint don't line up. I'm not sure if this is a KiCad or JLC bug, but I always seem to need a few rotations. Not that I've actually received a board with the incorrect rotation. I think the JLC PCB engineers do a great job of letting me know if something doesn't look right. So I'm pretty sure this step is optional, but better safe than sorry. The easy way to do it is to select the type of IC in the list and just press spacebar to rotate it 90 degrees until it lines up. Some footprints might not have a 3D model, so in that case it's up to JLC PCB to get it right. And I've never seen that go wrong either. And that's it. Now you just select the type of board for import purposes and fill in your info to have it shipped. If you're new to JLC PCB, you'll find your account preloaded with $123 worth of coupons. So you can even get a $30 coupon for a professional 6-layer PCB for just $2. That's a pretty sweet deal, and if you're working professionally with PCB design, the fact that you can get populated high-precision boards delivered in just a week is a must-have way to boost your engineering efficiency. Even with a pick-and-place machine in-house, it's hard to earn back the time it takes to set it up. With just a few minutes of work, you get a fully populated board ready to plug in. The minimum quantity to get assembled is just 2. So I have 2 boards and 3 extra PCBs. If you look down in the comments, I'm probably selling those pretty cheap until they're gone. And I think it looks pretty good. Of course, there's no firmware on the board, and by default, USB can't supply power to the microcontroller, so we need to get it hooked up. The footprint on the board is for a generic 5.5mm barrel jack, but the minimum recommended power is a 24-volt 6-amp brick. That might be one of the first things I would change about the design, because 144 watts is already on the high end of what these connectors typically handle. And if that's the minimum, a different connector is probably a good idea. The specific one in the project BOM is rated for 7 amps. But with a minimum recommendation of 144 watts and a maximum of 168 watts for the connector in the datasheet, there's not a lot of headroom. It won't catch fire, but it'll probably be warm at max load. If you're building it yourself and you pick a larger power supply, you'll want to make sure the connector you pick can handle the current. It'll probably work fine. I just don't love running connectors this close to their rating. And please do what I say and not what I do, because I do have a power supply capable of 230 watts, but unfortunately it's hiding behind this proprietary Lenovo connector, so I'll have to swap it for a barrel. The heat shrink isn't cooperating, and I'm 100% sure drawing 200 watts through the spare connector I had is not within the ratings. So I better make sure I change it before I start adding too many things. But for now, it'll be plenty to test the board works. Besides the connector, I'll also need to add a fuse later. But would you look at that? We have green LEDs for each power rail. The firmware for the board is a fork of Marlin, which is a mature G-code interpreter used for a lot of different 3D printers. The microcontroller has USB bootloader support, so it's just a matter of running a single DFU util command or open the platform.io project if you want to tinker with it. It depends a bit on your computer how to do it, but if you need help, feel free to stop by the Hackerspace Clubhouse on Discord that I link below. There's always someone willing to help. Since I don't have any of the mechanical parts yet, I can't really start building the machine itself yet, but I cheated a little bit ahead of time and got some of the parts that aren't available at JLC or I already have. You can get stepper motors from JLC MC, but I already have a few from a previous project, so let's use those. So far we have 3 axes, which means we can move up and down, left and right, back and forth. So far, you can't really tell from the parts if I was building a 3D printer, a CNC router, or a penbot, but the next 2 motors would certainly give away what kind of robot we're building here. They are NEMA 11 hollow shaft motors, and they're a little bit harder to source, but not impossible. The special thing about them is they are designed to have a pneumatic connector fitted to the top to allow us to pull a vacuum through the hollow shaft while still letting the nozzle rotate freely. Exactly what we need to pick up a part, rotate it to the right orientation, and place it on a PCB. Of course, a vacuum doesn't exist in a vacuum. Oh wait, I mean, we don't get a vacuum from nothing. I mean motors. We need motors to generate the vacuum. These are brushed DC motors with a diaphragm and valves that turn the rotation into the vacuum we need. The motors don't turn on and off fast enough to place components though, so we need something else to actually control the vacuum. To handle that, we have these two solenoid valves that'll happily turn on and off at a pretty snappy rate. It's also good to know if a part has actually been picked up or if it's dropped along the way, so for that we have these vacuum sensors and of course the cameras. We need cameras to compensate for mechanical tolerances if we want to place 0402 components. And that we absolutely do. Since the bottom camera needs to handle both tiny and big components very close to it, it needs a wide lens. The top camera, on the other hand, only needs to see fiducials and component pads super clearly, so for that we need a longer lens. To get the maximum out of those features, I picked two 1080p cameras, but with a 2.3mm and a 12mm lens. If you're a little bit into cameras, you might say, 12mm, that's super wide! But actually, on the tiny camera sensor of only 6.2mm diagonal, the 12mm with a crop factor of 7 is the full frame equivalent of an 84mm lens, and the 2.3mm is about a 16mm lens equivalent. If the 12mm turns out to be too aggressive, I have a 6mm too. We'll see. Now, since the vacuum sensors aren't the cheapest of components, and I'd like the opportunity to swap them, I'm thinking socketting them might be a pretty good approach. But as it turns out, I don't have a wide enough 6-pin socket. So if I want to swap these later, the solder's coming out with them. Oh well, hope they work. And with those in place, I believe that's about it for the electronics until I start thinking about adding a fan and some component feeders. But that will probably be a while. I ended up paying about $150 for the cameras, pumps, and the hollow shaft pick-and-place motors, and I'll put links to those specific parts in the description. But I've also forked the project so I can share my changes to the PCB and links to all the BOM items I find at JLC. Next thing on the list is the wire harness, and to be honest, it's one of my least favorite things in a project. Because compared to a PCB where adding another trace costs the time it takes to draw it, every single physical wire is its own little problem, and even with the right crimping tools, it takes quite a bit longer than drawing it. The board uses JST PH 2mm connectors, and I got a box of those. But since my tools aren't perfectly designed for those, I'm going to be spending a decent amount of time crimping wires and re-crimping wires. But with some wires in place too, we can start checking everything works like it should. Oh, I forgot about some of the electronics. We're still missing the end stops and the end stop PCBs. But luckily we can still test the motors without end stops. This is what OpenPNP looks like without the cameras attached, which does seem a little bit boring. But would you look at that? Right out of the box, we can get motors running in every direction. I can't seem to find the right button, or maybe it's just not there, but with a little bit of manual G-code, I can still command the rotation motors to do their thing. Unfortunately, they both seem to have a bit of runout originating at the motor mount. Oh well, probably not something we can't calibrate away with the cameras. Speaking of manual G-code, I also need a bit of that to manually control the solenoid valves. Not that you can see anything going on, and they barely make a sound. If I try to breathe through them, I do feel it instantly cut the flow, but I'll spare you the visual of that. The vacuum pumps, on the other hand, must be the reason this whole setup needs a box, because those things are loud. And they work. Probably a bit less noise with the pneumatic tubes connected and everything. So, I've started building a P&P machine, and I don't think there's a way back now. Next time I'll get some of the mechanical parts, and I've started 3D printing some of the parts myself. But I'd really like to try JLC's 3D printing service because getting a lot of small parts printed without giving it much thought sounds like a time saver. I don't know if it'll be picking or placing anything next time, but I hope you found my new project interesting, even if it is a bit different to my other projects. I'll probably end up hacking tons of things to this when it's done. Or most likely before. Either way, thanks for watching.